Okay, so today we have Andrea Censi from ETH talking about designing everything together.
Yes, and it's designing everything together, but also designing everything together. Right? And it's about resources and design theories. And some of this work is joined with David at the time when I was at MIT, so 2015-16. And so I want to start talking about resources, right? And how I want to claim that math actually was motivated at the beginning by resource accounting. So suppose you were a sheep herder in 5000 BCE. You bring out your sheep during the day. At night, you should make sure that you have the same sheep that you started with. How do you do it? Multiple ways, but one way was the rope method. So you take a rope. Each sheep that goes out, you tie one knot. Then at night, each sheep that comes back in, and it doesn't matter which sheep, probably you know the name of the sheep, but it doesn't matter, you remove one knot. So if you don't have any knots left, then everything was okay. If there's knots left, then you need to go look for the sheep that's missing. Right? And I was looking, this is actually very, very modern, right? Because in there, you can see, you squint your eyes, you see the definition of natural numbers and the modern definition of the cardinality of a set, right? Through isomorphisms of the elements. Okay, now let's jump forward to 3000 BC. Now you are the heir of a sheep empire in Babylon, okay? So now you have a lot of riches to count, and so knots are not good anymore. And so you have to invent something like that, something, positional number systems, which I see as very much like accounting resources in a compositional way, right? So each symbol signifies some resources, and then the symbols together is the resources together, and then you can group them in a compositional way. So the next innovation came, after the first century, was the Indian invention of zero, right? Which is this new abstraction of no resources, right? So now the isomorphism is not between the signs that you do and the elements, the things, but between the signs and the set of things. So this is one level of abstraction of both. Other classical math was motivated by resource accounting. So in ancient Egypt, you probably be like a scribe. And you had this problem that every year the Nile is flooding and you need to retrace the boundaries in a fair way. So resource accounting, right? How do you do it? Well, you've been trained and you know a lot about shapes. And you know that, well, there's a field, but that field is also represented by some shape on your paper, papyrus. Right? And then you know that these shapes, you can transform one to another. Like you can kind of rotate them. But also you can kind of join them or divide them, and all these operations are preserving something, right? So you kind of can go back and forth between shapes, but also something is preserved, right? So you also have this idea of invariance of resources, right? Okay. So next step is another big step. So now it's India. It's 600 C. And you start to have taxes, you start to have commerce. So what you need is negative resources, essentially, right? So although number systems were with negative numbers existed, actually we have a historical record of this mathematician called Brahmagupta in India, which gave the rules for negative numbers, right? So now it's interesting. There's three things. There's something called a zero, something called a debt, something called a fortune. So fortune is positive, a debt is negative. And it gives you, the rules of how these operations apply. So addition, subtraction, product, and quotient, right? So also very modern, right? Because, you have now the notion of an operation and the notion of kind of identity of an operation. And also, it's giving you like the homomorphism, it's computing the sign of these things, right? It's giving you the rules in the next category, right? Okay, so this was very beautiful. Math at the beginning was about resource accounting. And then, what happened? Well, okay, so then kind of math moved on to other things, and people started with their algebra, Diophantine equations, and they went in search of truth and beauty, and kind of lost track. So for us engineers, now we just do like the let's do the time warp right, to the 21st century, to the present day. So what's the problem now? So suppose it's the 22nd century, you're a sentient AI trying to bootstrap yourself to singularity. Oh, wait, so I think this is a kind of overflow, went a little bit too far. So let's bring us back 1 century. So suppose that you are a few hundred engineers trying to design a fleet of self-driving cars, which is my personal experience. So as engineers, we need to develop these very complex systems that have many components, right? So you have actuations, you have software, you have hardware, you have batteries, you have rules, law to take into account, and so on. And we feel really unprepared, right? So that is the personification of 21st century engineering malaise, right? So it's just painful, right? What are the problems? So many components, so many choices to make. I have these computers. These computers are really not helping me too much, right? We just don't understand what's going on, right? Well, what's the diagnosis, right? Now, my dear, it's simple. What you lack is a proper theory of co-design. Right? This is what I'm going to talk about today. Okay, so some references here. I think the best references are, well, the book by David Brennan, right? I also put a couple of papers, more like engineering-like, by me and my student Joelle. And there's also like the, the recordings of the lectures that David and Brennan gave 2 years ago, and also online there's also the same material taught by John Byers, like online. So there's plenty of opportunities to learn. So today I want to focus more like on the motivation, rather than going deep into the topic. So this actually, let me first show you how I explain it to engineers. Because I think if you want to apply category theory, you want to go out, evangelize. So this is the level which an engineer would understand. And then we get to the actual math. So the abstraction here is that we're going to think about the same problems and functionalities and resources, right? So, and just like Brahmagupta, we're going to think about positive things and the cost that we call the debts, right? So we're going to abstract the same problem as a relation between the functionality that's provided and the requirements that are needed. And now these things are called many different ways in different fields. These are called functional requirements, the desired behavior, the specification, that's on that side. Or in this side, we have the costs or the dependencies. And so everywhere, software and hardware, you have these two types of things, right? So we're going to think about this as partial orders. Why is this complication needed? Well, it's because maybe each of those could be scalar, right? Maybe one is weight, one is dollars, right? But once you have at least two, then all of a sudden it's a partial order, right? So partial orders are needed here. So an example, suppose that we want to consider the choice of a battery in our robot, right? So for example, the requirements, the resources, the costs here are the cost in dollars and the mass of the battery. So these are things that you need to pay, and you'd be happier if you didn't have to pay them, right? If the battery was cheap, you would be happier. If the battery didn't weigh anything, it would be better, right? So what's on the other side? Well, so you use a battery to provide, some current at some voltage to the other parts of the system, right? And now it's a little bit of modeling exercise now to give you some more examples, right? The point I want to make is that this actually works in many domains. In many domains, you have the thing that's producing something and requires different kinds of resources, right? And then the next step actually is going to be like the monotonicity, right? So you expect that if you give David better coffee, you get better theorems, right? Or at least it's going to be like non-decreasing, right? So if you give better coffee, the theorems will not suffer, right? Okay, so the next step now is to understand monotonicity. So this is where the Boolean profunctor will come about. But like in a visual way, you can imagine now, imagine these are like multidimensional spaces, like compressed to one dimension. So we have the F and the R, and they're partially ordered. So what we expect is that some combination will be feasible, some will not be feasible. And we expect that, well, if you give me maybe something is not feasible, but if you give me more resources, what it might become feasible. Or, if something is feasible, but you increase the requirements, is gonna maybe what could happen is that it becomes unfeasible, right? These are the transitions that are possible, which means that we're looking for feasibility as a monotone map between f op, because it's kind of reversed, R and bool, right? And that is the definition of a profunctor. Now, the other thing actually that we care about is another set. So not only we have functionality requirements, but also we have implementations. So this would be like what's inside the thing, right? What are the choices, the decision variables, right? So maybe that's the set of all possible batteries that could be invented or that are on Amazon and so on. And so that would be like the proof relevance part, right? All right. So this is what can an engineer understands. Now I'll do it again in a more mathy way. So first of all, is proof relevance relevant to engineering? Yes, because we don't not only care whether something is possible, but we actually need to build it literally, right? So we are literally constructive. So actually now, morally, the category that we're going to talk about, like the morphism, actually you can think about morally being generated by that kind of spans, right? So you have a set of implementations, any set, and then you have two posets, functionality and resources. And then for each implementation, you can tell me what are the resources required, what is the functionality provided. Okay, so this is a way to make it also very constructive, right? Because three sets and two maps. So now, if I have that, then I can come up with the answer to the question. Okay, if you fix a functionality requirement, which implementations are feasible? So that's a map from f of R to the subsets of J, right? So just looking at the implementations that are feasible. Okay. So now, for the purpose though of global computation, the components all interact through interfaces. So the implementation is like an implementation detail. So that's why actually we currently care about Boolean profunctors. So what I'm doing, essentially well, I have that thing that gives me subsets of implementations. Well, I'm asking, is it empty or not to get to bool? And so now we're going to live with Boolean profunctors, but that's kind of the moral origin of these Boolean profunctors. So there is this category DP, also known as Phias and Prof bool, but you should realize that DP kind of rolls off the tongue a little bit better. Right? So the objects are posets, the morphisms are these Boolean profunctors, and we also write them like this. Okay. And then later, actually, we're going to need a little more assumptions for the computation part. We're going to ask that actually we have DCPOs instead of just posets, right? That's just for the algorithms. We did make a mistake, I think, in this formalization, because then I learned about linear logic, and they have similar, different thing, but similar, right? They would write it like this: if you have some resources that go and produce some functionality in this direction. So we had 50-50, we kind of got it wrong. Okay, so now if the rest of the talk is going to be boring for you, I suggest you can do all the construction we're going to do with spans. Right? You can think a little bit more about the career of the isomorphism. Think about those things as propositions. Right? You can think about the fact that all this is completely symmetric, and and this is completely reversible. Okay. All right. So now let's go back to engineering land. What is composition in this category? So I have something that needs something. For example, there's a chassis that needs some torque. I have a motor that produces some torque. How do I connect them? Right? So I want to define this composition operation. And I want to give the semantics that the resources required by the first system, well, they must live in the same poset as the functionality provided by the second system. And this should provide enough. So this is not going to be strict. There could be some slack. Like this should be enough to provide those. Okay, well, how do I do it? Well, you give me something from A to B and something from B to C. I'm going to produce you something from A to C. So when I write that vertical line, it means that from what's above, I can produce what's below, right? And that is like the graphical notation that I am going to use. So how do I do it? Well, we have the definition of these things as profunctors. So given one profunctor like that, one profunctor like that, I need to produce a profunctor like this. And so this is kind of standard way to do it, and nothing fancy here. The way you do it, essentially, you try to find something in the middle. You try to find labels, like you go here and here, that make everybody happy, right? So now you want to be careful. You don't want to say, okay, there exists something, because that's not constructive. What you just say, you can say is that, well, you can integrate over all possible things that could be in the middle, and so you have kind of preserved like the constructiveness of the construction. Okay, so now the next thing would be what is the identity? So we have an A. Now for every, I promise you that for every A, I can find you, which is a posit, I can find you this profunctor. And in terms of polymorphic things you can come up with, there's nothing much that you can use except you have the order of the posit, right? So in fact, the identity is essentially the order on the posit. Okay, so now once you have these operations, I'm going to skip over like products, coproducts, traces, monadal structure that it's as you expect. You can do composition. So as an engineer, it's very fun to have, think about these blocks, and then now I can put them together and compose, describe the big design problem out of components, okay? And then being able to abstract it. What was surprising for me, and now it's obvious because by construction, the composition, this is a category, so the category of monotone profunctors, right? Boolean profunctors, so everything is a Boolean profunctor, right? But for me, it was interesting to discover that indeed you could have these guarantees on each single components, and then everything together was monotone. This was surprising at the time. So the role of feedback is also interesting. So we can do traces. And now the traces actually, they describe kind of the irreducible complexity of design. So designing is difficult when you cannot decompose. So for example, if you have a battery, so you have to put the battery on the chassis. So the chassis must carry the battery. The motor must move the chassis. The battery must power the motor, right? So that means that because there's a cycle, you cannot choose those things independently. This is the first time in engineering that you find like definition, what this could be like the reducible complexity of a design problem. In a little bit more like a mature way, you always have, as an engineer, you have the budget that you use to buy components that implement behaviors, and the behaviors, the budget must be specified by the behaviors. Right? That is why engineering is complex. Okay, so recap. You are trusting me that this is a trace symmetric monadic category. Series parallel feedback, engineering terms. But there's also more structure. So in fact, it's locally posetal, and it's actually enriched in a bounded lot. So means the following, that now I can fix like an offset from A to B. I can have a top that tells me everything is possible, a bottom that says nothing is possible. And then I can have two other operations to get new morphism out of old morphism. And now I don't like the graphical notation. I need to find something better, right? But these are things that preserve the signature. So you give me something from A to B, two things from A to B, I get you another thing from A to B, right? So there is essentially the and the or, right? So the union would be that now you have two different options to do something. The intersection would be that you need to be able to do something in two different ways, right? So you need to convince two different experts that something is feasible, and you have this, this order on that. So it's a very self-aware category, right? Because the objects are posits and the offsets are lattices, and so it's all very like basically everything is true. Mostly everything is true. Something sounds true, it's probably true. Okay, so I want to talk a little bit about the algorithms. About the querying, although I imagine this is a little bit of less interest, so I'll go quick. So from the point of view of an engineer, what you want to ask is, well, Either you fix the functionality, you want to minimize resources, or vice versa. It's all symmetric, so it doesn't matter which direction we can go. We could also do both at the same time. So we're just going to choose one direction, which is, given the functionality, what are the minimum requirements? So here, if you want to start computing, you need to have a little bit different representation, which is a bit, it's computable, right? So that was like a feasibility-based representation. Now, first of all, you need something computable. I use anti-chains to represent essentially upper sets. And you want to describe each component as this map now H that says, for a given functionality, I give you some options of resources that make the problem feasible, right? So we need also that deposits need to be like pointed, directed, complete partial orders, and the maps need to be Scott continuous. It's going to be like a clean iteration, spoilers, right? So we need to start from something, and we need to be able to converge to something. Like if you've done analysis, think about Cauchy, complete metric spaces. It's the same thing with partial orders, right? So this is domain theory, it's called. Right? So I just want to give you now if you are in applied mathematics department, then we'll be very, very careful about specifying the optimization problem, right? So I need to give you the decision variables, which essentially are all the labeling that's not in there, like on all the edges. The objective will be minimizing R. Big min means finding me all the least elements, right? The constraints are for each node, like each node should be happy by itself, right? And then for each two nodes, two edges, well, these should be happy about what's provided by this. So this is interesting because it's not convex, not differentiable. It's not even defined on continuous spaces. I didn't test some continuity, for example. You can solve this. Now, you can kind of have an intuition that where you have problems are loops, right? Because if you think about parallel or sequential design, you first solve one and then solve the other. If it's parallel, you solve both at the same time. It doesn't matter. So the real problem is understanding what happens with the traces, right? And kind of the theorem was, well, suppose that you have like the trace expressed in this way, it's a kind of Conway form, right? Just equivalent, so not funny business here. So essentially you can show, and you know that H there, like by itself, the H, the solution from functionality to resources. And then the idea is that, well, actually, I can find the H loop for everything, and as the least fixed point of a certain map, which is this thing which I don't have an intuition for. But the idea is that you can you start from the bottom, right? Like Jay-Z, I guess, and then you go up, right? So it's like this is clean iteration. So you find these things. You start from the bottom, and then you have a way to go up. And then you converge to something finite, or you converge, to the top of the deposit. In the case, it's like a certificate of infeasibility. Okay. So the nice thing is that the complexity of this actually depends on the minimal feedback arc set. So it doesn't depend on how many choices you have in each component. It depends on how interconnected they are. So minimal feedback arc set is the number of arcs that you need to remove all cycles. So what you do, you want to basically represent everything as trace of series parallel, series parallel, series parallel, in a way that this thing is the smallest possible. Okay. So this is a quantitative way to say what's the complexity of the design. Okay, so this was the description of a mathematical theory of design. So it's compositional, it's computational, it's collaborative because different experts can look at different things and then put them together. And so the part that I really care about a lot is actually, okay, now that we have this theory, how do we bring it to the world, right? What would be like a web of co-design? So I just want to give you the first step, which is a description of the language for this co-design. Just want to give you like an idea of the syntax of this, right? So there's actually a website, and there's a demo, and there's a manual, so you can look at it. This is not a language for category theory, just that Ivan Patterson was talking about last week. It's about this particular category, right? And it should be as easy as possible. Like, so I have this thing, that's an actuator. The engineer will write, this thing provides lift in Newton, requires power in watts, and this is the relation that must be satisfied. And this language is really, most of the times, actually writing something non-monotone is a syntax error. So it's really like at the syntax, the monotonicity is really at the core of this language. Well, okay, so you can look on the web. I just want to show you that just like every language, you can do compositionality, right? So you can define sub-things, lambda functions, and then you can compose them, right? The interesting thing, it's very interesting to write a compiler that can do for everything that's reversible, right? So usually you have a tree, right? Lambda calculus, it's a tree. Right? Here it's like a graph that you can go into two different directions. Okay, so now a little bit more advanced work. You can think about uncertainty in codesign. So the objects are posets that we think about that have a bottom, right? So now we think about them as eggs, and we saw the sets are lattices. So everybody knows that a lattice is represented by an egg, right, with the top and the bottom, right? So we pick one morphism, right, and then we pick an element there, and then we get the minimal solutions here, right? But also that's a lattice, right? So there's all this the structure in there, right? So top and bottom intersections and unions and things like that. So what you can do actually is instead of thinking of a particular point there, you can think about an interval, right? So you can think about I'm going to just bound that thing by an upper bound and a lower bound, and then I'm going to think about intervals of the piece, right? And now I can solve, for the optimistic thing and the pessimistic thing, and get two other results. Turns out that all these operations are composition operations are monotone as functors, right? So essentially, you can have like an upper bound and a lower bound will give an upper bound of solutions and a lower bound of solutions. So in fact, there's a category on certain DPs where the objects are posets, and the morphisms are ordered pairs of morphism of DPs. And I suspect that next year, when I understand monads, maybe there's a monad in there. But see you next year. So in practice, the user can say, the energy density is between this and that, right? That's the power of this representation, right? I don't know which one, but it's between A and B. And then the answer now will change. So without uncertainty, the answer is like, you need $230 for this. If you have some uncertainty, we'll tell you, well, the minimal cost is going to be between 220 and 240. There's a lot of uncertainty. It's going to be, well, it's 220 in the best case, but actually in the worst case, it's not even feasible, right? And from the computational point of view, another motivation is that you can use uncertainty to relax the problem a little bit, right? So this is like the blurring of the problem. So in fact, it's easy to come up with things that are not computable. For example, if you have just f time, r1 times r2 equal 1, so yeah, these are the possible solutions, right? Okay, that's an infinite anti-chain, so you're already dead if you want to compute, right? So what you can do, though, is that you can create a sequence of successive approximations that have finite empty chains, right? That will converge in a very nice way to the solution, right? And they're all finite. So in fact, the implementation level, the category, it's a category of shrinking sequences of pairs of DPs, right? That is actually what's implemented. All right, so now this is what I've done. Now I want to use some time to think about next steps together and things we could do together. I'm here for the week. So I want to propose like 7 more sketches for resource theories, 7 more. So this is not work in progress. It's going to be a little bit informal, right? But I think it's interesting. The more I work about this, the more I realize that actually every engineer has a trace monoidal category. Everybody has one, right? And the functors, and look closely also at natural transformations. But some more advanced stuff is actually relevant, right? And I'm really enjoying kind of learning about category theory in this way, like motivated by this field. Okay, first one, monoidal and tropical resources. Well, so some of the things we mentioned, like money, like watts, are things that you can add together, right? So that's a little bit more structure. So, well, you're going to assume that you have a monadal structure that's compatible with the order that you have with deposit, right? And then now you have many things for free, right? So, for example, the DP that says A plus B plus C less than A plus B, then it just like it can be created by simple building blocks that are available. You can also do things like this. So you have a DP from A to B. From that, I can certainly put n of them in parallel. So I get f of n from a n to bn. But then also I can use the plus to kind of compact them, right? So this is a DP that basically divides the work among n DPs, which sounds like a very useful thing to do. The thing I don't understand is actually sometimes I need to sum, sometimes I need to do the max. Like the sum of the times, sometimes the max of the times, sometimes both in the same diagram, right? So I suspect that this is where the tropical comes from, right? That actually also looking at this a little bit more structure like this would be very interesting for DPs. Okay, sketch number 2, homogeneous resources. To make a car, you need 4 wheels. Those 4 wheels need to be the same, not the same wheels, 4 different wheels that are identical, okay? Or, if you want to go to a party, we need to dress differently. We need 2 clothes that are different. Some people worry about that, right? So how can we put that like in a framework of resources? Well, okay, so take a type, and suppose that you have like equality and apartedness, right? So you have, you call like this x equal a y. That's the type of the proofs that x and y are the same for what concerns the a-ness of x and y. And then also you can say, well, x negated equal a, y is the type of proof that they're actually apart in some sense, right? And I don't judge what you choose for equal and apartedness, you give it to me. And then now you can define these interesting types, right? So you realize actually the proofs themselves are resources, right? So, and then you say, well, let me define, for example, a equal to. That notation means that this kind of dependent type notation. So you give me an x, you give me a y, and you also give me a proof that x and y are the same as a's, right? Or you give me the other one would be like a not equal to. So you give me an x, you give me a y, and you give me a proof that they're different, right? And this actually captures a lot of the things that we care for resources that need to be similar or different. And they're interesting stuff. Like, for example, interestingly, it seems that these 2 things commute. Like, so if I have 3 equal elements of 2 things that are different, it's actually isomorphic to having 2 different things or 3 things that are equal. So this is kind of fun. I think it's an interesting type to implement, for example. Okay, so now let's go a little bit higher order. Higher order structure. So now we start thinking about templates, for example. So for this purpose of this, like let's call template as a diagram with a hole, right? It's something where there's some space to put something to get a new one, right? So, and the type there means that you have to put inside something that goes from A to B, and the output will be something that goes from C to D. So what you can prove is the following, that if you look at that map now that's a map between omsets, right? Omsets AB to omsets CD. That's actually a monotone map, right? So that's paused there. And why? Because those composition operations are all functors, essentially, right? But also, you can write every monotone map between omsets as a template filling operation. And this is because we basically get essentially so many composition operations that we can do if, then, less than. We can do everything, right? So essentially, it's very self-aware category, you know. Also, you can do recursion, right? So where you can put the same thing inside. And this works because you actually have a bottom to start with, and then this thing converges, and this is like standard domain theory. You know, that's more colorful domain theory. Oh, I call it, right? Okay, but actually, when I say higher the structure, actually that was a misnomer because this category is actually compact closed. So a compact closed category, basically all the higher structure collapses. There's no higher structure. So in fact, you can take that template with the whole A, B to C, D. That's also a DP because that thing is something that will produce a CD if you give it an AB, right? So it's a DP between these two posets, right? But also, you can either apply that, or you can kind of start moving wires along. This is all flattened, right? So, well, of course, you have to take like the polarities, right? So C and D, still green, still red. And here, that's kind of the negative part, right? So there's a switching. So you have a B and an A, right? Or you can go from here to here just, by pulling the wires, essentially, right? So, okay, so it was a little bit disappointing because there's not much higher order structure, right? There's none, essentially, in some sense. So what can we do? Well, we can make our life more complicated. So another option is putting a little bit of linear logic in here. Who knows what linear logic is? Okay, so who doesn't? It's like a trip. It's really like look into it, right? It will blow your mind. So in classical logic or kind of programming, or classical stuff, you have this inference, right? I give you an A. If you have an A, if you have something that goes from A to B, either an implication or a function from A to B, then you can turn the thing, and then you get a B, right? But you still have the A and the A to B, right? So it's just like the metaphor for classical logic is that you're walking around and finding things. You found an A, you found the way to go from A to B, but then you didn't take it, right? By linear logic, actually, you destroy things. So the basic rules is this. So A lollipop B, I call it A produces B, is the type of single-use machines that hit an A, produce a B, and then disappear, right? And so from these two, you're only left with B. So it's a trip. Many things are really interesting, in particular for co-design. You have two multipletives, two additives, an involution, 4 units. That's everything here. But for example, there's a distinction which is very important for engineering between A and B. There, A with B means that you can choose to have either A or B. So it's something that you can transform into an A or a B. But A plus B, somebody is choosing if you have an A or a B. And that's like a really important concept in, not only in design, but also like communication systems and things like that. So I hope this makes you curious about linear logic. So my problem in particular is the following, is that I say, okay, so I know what is a DP. I know what is a linear logic. What's the list? What's the listing that kind of captures both, right? And this is something that, for example, I know this. So if I know that resources can be copied and discarded, and there's no distinction between external and internal choices, then I get DPs, right? Here I'm trying to understand it. So I know that linear logic, all the posets are bool, right? There's not really posets, and there's no proof relevance. So that's a question that I have. Okay. Next thing, temporal resources. Suppose that I want to keep track of the time it takes to do something. Very important in engineering, right? So I want to do something like that. I want to think, well, so if I give you an A at time t, then you give me a B at time t plus delta, right? So I want to somehow keep track of this delta, right? All right, so this is going to be a little bit informal, right? I think of that as basically subtypes, but this could be done differently. So I want to refine the home types by time, right? So we still are going to have an identity, and then it's going to be like, if you have an A, you can give me an A in 0 time, right? So that's still there. But then, you know, A, if S is non-zero, might be uninhabited, right? For example, if you have ice, and then after 10 minutes, maybe you don't have ice anymore, right? Maybe the axiom is that if you have ice, after 10 minutes you have water. To actually keep the ice, you need to have the ice and the fridge, and the space in the fridge, and then you get the ice. And it's very, so this is like all manufacturing work is like this, right? So this is very, very practical thing. Composition works the same it's expected, right? So nothing funny there. However, kind of the monoidal structure, it's weird, right? Because now you can put two things in parallel only if like they have the same duration, right? So it's not entirely monoidal. Like each slice is monoidal, but it's not monoidal as a whole. And okay, so the good or bad news is that now you have a lot of second order structure. Like nothing collapses anymore. Like if I had to, you know, if I have an A, I need to wait for alpha, and then I can do the thing that gives me from a B to a C in beta. These things are not going to collapse, unless, you know, everything is like non-perishable in some sense. Also very interesting, and we go back to Brahmagupta here, talk about money and interests and loans. And also negative time, which is not quite equivalent to negative resources. So for example, suppose that you have promised me that you'll give me $10 tomorrow. So what I have your promise there, which is something that from nothing, one means nothing in this context, in one day we produce $10. What you have is the opposite. What you have is something that in one day will produce minus $10, which also it's something that produces in 0 time, basically your money disappears in 0 time, right? So that's like the negative resources, right? But if you think about lending over time, then you need negative time. Suppose that now, if I can lend you, I'm the lender, so I lend you $10 now, I can have $11 back later. So I can put $10 now, in 1 week I get 11. Now the ability to borrow is different, because it's like this, like if I can repay you $11 in 1 week, I get $10 now. So $11 produced in minus 1 week, like $10. And so you see, there's actually, in linear logic, like there's actually 2 ways to negate things, right? There's like giving and taking, and then when this thing happens, right? And of course, you know, you can do economics. Economics, well, it's not all, it's a part of economics, right? It's like, so if you give X dollar at time t, is the same as, I should consider them equivalent if I have access to credit, to having X dollars times alpha delta at t plus delta, where alpha is the interest rate, right? So it would be interesting to, you know, co-design modulo this, right? That's so interesting. Okay, number 6, and we're almost done. Spatial resources. Okay, so, well, after time, and now the space, right? Very interesting also for manufacturing. Sometimes it really matters if you have 2 things that are separable or not. Like, for example, having like a spoon, a knife, and a fork is different than having a Swiss Army knife that is, you know, a spoon, a knife, and a fork. Not only because you cannot use them together, but also because they are constrained to be in the same place, right? So now we can have different tensors, right? So we can define A squiggle B as 2 separable resources, A connected to B as 2 inseparable resources, and A hates B, I want to say, 2 things that are constrained to be apart, right? So now this is very simple. We can either be close or apart. For example, 2 Wi-Fi access points give you a certain bandwidth, but you cannot put them nearby, right, because they don't work. There's interference, right? So very fun. This thing, it's a linear distributive category twice over, because there are 3 tensors, 3 monadic structures, very happy by themselves. But also, there's this order, you know, there's like this idea of strength of tensors over another tensor, right? In linear logic, you usually have 2, right? So you have the times is stronger than the par, But here there's 3, right? And so what does it mean that there's strength? Is that you can exhibit this morphism, which make it like kind of distributive in a linear way, right? So the way you can read this informally is that, well, actually, something like this, I can use it as something like this, okay? So, for example, if I have an A and a B and C that need to be together, I can certainly use it as a C that needs to be close to either a B or an A, right? So the interesting thing for me, which really the limit of my capacity, is that, well, actually, you can do this a little bit more generally. You can say, well, let me take a metric space. Let me say that I have some notional distances between sets in these metric spaces, right? Hausdorff distance or whatever. And then there's an entire family of, you constrain A and B to be at most at least M, at most M from one another. And those are like 3 particular cases when you have like, close and far. There's only 3. Very interesting, I think. Also, you get into this and you can think about, well, let me refine the axioms, right? Because if I have an idea of being close, then if I want like a machine AB to produce a B from an A, it's reasonable to expect that A must be close to the machine, right? The other thing I also thinking about this, the thing I really don't understand a little bit is the treatment of subtyping in category theory, because actually, type theory, we're very careful about the types. Category theory is a bit like compacting everything. So, for example, so take this to be, let's see, take this to be the usual tensor product, right? So, if you have a morphism from A to B, a morphism from C to D, you can put them together, and you get a morphism from AC to BD, right? This is a monoidal category, right? But that's in that direction, right? Because actually there's another way, assuming everything is symmetric, there's another way that you can go. Because you can take something from C to B and A to D, and then you put them together, kind of you forget which one it is, right? And then, because of the strength, then you can do the same with other tensors, and then you can work out this relationship, right? And sometimes I feel that, being a little bit more careful about the subtypes here might be helpful. Certainly, it's helpful for me, like in the implementation. Okay, the final thing, negative codesign. You might not realize, being this in this mathematics department, that we live in the real world, and in the real world, it's kind of boring. There's like this thing called conservation of mass and energy, right? So we talked about codesign, profunctors in general, but actually, if you can think about plausible in this universe profunctors, and for me, that's the axiom of the real world. So for any profunctor from A to A, something that produces an A from an A, well, necessarily it must be less than the identity, because you cannot produce something from nothing, right? I mean, you're missing something, right? Okay. And then you say, okay, this is cute, fine, right? But actually, if you put an axiom like this, it changes the entire theory, and because of the following, it makes it like non-monotone in some sense. So when you give me like a profunctor from A to B, what I think about it, you tell me something positive. It's good. Oh, thanks, another profunctor, right? So more things that I can do, right? More options, right? So you tell me something positive about what B I can produce from A. But now, actually, you're also telling me something negative about what A I can produce from B. And why is that? So here's the thing. Like it's a usual like 2 lines proof, right? So you gave me a G. Now, for every any H, I can form G then H and the H then G. And these things are from A to A and from B to B. Every morphism from A to A must be less than the identity. So necessarily for every H, these 2 things must be less than the identity. And then I was thinking, oh, okay, this is good. This is the things I can do with H. No, actually, these are lower sets. These are constraints on A. If you look at the kind of polarities, essentially, you gave me a G in the one egg AB. And from that and the axioms, you get like a lower set of what's possible to do in OMBA, right? So, which means that, so sometimes, in computer science, you get more facts, for example, like more facts is always better, right? And then you don't revise old facts from if you're consistent, right? But here, actually, you give me a positive result, it's also an impossibility result for something else. And so this means actually we're looking essentially only half the theory. Like, you cannot look at one egg by itself. You really should look at like the two eggs together. And of course, this is very important for computation, because it's about impossibility results. Okay, so that was my presentation. So conclusions. I want to say, like, what you're doing here, this nascent field of applied category theory, very helpful. Like this idea of translating maybe math that's already out there in category theory, but kind of chewing it a little bit, applying it to examples, making it understandable, giving some motivation for engineers like me, other engineer-like entities. I think it's very, very important. And the more I read about it, the more I enjoy it, right? Yeah, so I really appreciate what you're doing here. Thank you very much.
Question? So, yeah, thanks for the talk. The first thought, more of a thought than a question, is this reminds me a lot of propagator networks from Jerry Sussman and Alexei Radul. Just, you might want to look at that if you haven't seen. Because this sort of like setting up a reversible graph structure and finding a fixed point solution to some network of constraints, like that's sort of the, I learned about that in undergrad. So it looks similar to what like your formalisms might help, and I'm trying to find like where the extra power might come from. But as for questions, there's a couple situations I want to know if this captures, or if this is in your next steps. One, so this assumes that you can like write down the whole constraint set at the beginning, right? Like what functions you want and what resources you might need. Sort of like this all has to exist in one diagram. In the real world, maybe different departments of your company know these different things. So that's number one. Like, how do you actually imagine merging that, or is that a problem for practice? But the more deeper question might be, what if those constraints are not simultaneous? So what if a decision made over here actually causes a new structural constraint somewhere else? Maybe that will happen. And then the other thing is, these are monatomic resources. There's very physical mass and energy, but what if it's something more information or intelligence driven, as opposed to like, your car has mass, but your car also needs to know like where the pedestrians are and what the routes it's going to take. So can this relate to sort of discrete problems also?
Yeah. So the first questions before. So actually, what you have in mind is the main problem also have in mind, right? So this idea that different people sitting somewhere different, somewhere different, how can they communicate effectively, right? And so the thesis here is that for some domains, basically, you don't do decisions locally, but locally you produce one of these models, right? You say, guys, our department thinks these are the options, not committing on any answer, but this is our profuncto, this is what we can give to you, right? And the other department will do the same, and then you can put this into the same diagram, and then the algorithm will optimize everything at the same time. So, and then in practice, that is very important. The social part and also the technological part. I'm also working on that a lot. Is well, for me, it's about having this formal language that somehow, just like a Python library, you can publish it and then you can import it. It's exactly the same idea. So that somebody then now asks for the library for each department, and then put them down together. So that's the challenge, my current challenge, right? So how do you get all this theory to actually matter in the real world, and think about the workflow? The second question, so I work in robotics, right? And there's a lot of co-design in there. If you think about that, has to do with information and intelligence, right? For example, we have partial orders about behaviors that the car can. So the specification for us is like things that the car should do. Right? Another positive is like what sensors you want to put there, what information you need, right? And so now you know that what you want to find for a given behavior, the least sensors that you need. The computation part, so this is information theory. This is like control and information theory. Computation part, very important, very empirical, right? Because how long does it take? It depends on the substrate. So you cannot think about algorithms in the abstract, right? It really depends on the substrate, CPU, GPU, whatever, sticks and stones, whatever you have, right? So there, I think it's a little bit more empirical, right? So what you think about is like libraries of software components that are tested on every possible combination of CPU and GPU, and now then you can use that empirical data to make the decisions about what to put together. I hope that answered the subset of the question.
Is that the last part? I mean, I'm thinking of something where you decide I want this functionality, therefore I'll need these sensors, but also you have, well, therefore I'll need this code. Like I'm going to need this logic to somehow.
Yeah.
So is it going to write the code or?
Well, you can. So this is about putting this together, right? So you need to start with something that's available. So you could have like a catalog of Docker containers, each implementing an algorithm, each having like a price tag. This one costs $10 to license. This one costs 1 cent per iteration. And then from there, this is how you put things together, right? So I think now in the future, it's really about looking at all the CAD systems in the world, like because each domain has its own like computer-based design system, and basically this is the common interface. This is how you glue everything together, right? That's kind of the hope.
Other questions? Yeah, thanks for giving some talk. I was thinking of how you design things. It occurs to me that they're very rarely satisfied with proofs that the designs are correct. What they really want to see is like the thing actually built and tested. And sometimes the tests fail, right? And the thing blows up in your face. And you get one bit of information about your design, and you know it's wrong, but perhaps you don't know where. Right? So in this construal design, does this offer us insight in like how to, like if I have a design and all I know is that it's not feasible, right? Does this offer me like a point of view for going back and identifying like the candidates for failure, or can I back propagate these uncertainties?
Yes.
Things like that.
I think so. The easy question is: suppose I have a diagram, and I ask some question, and it's not feasible. Okay, what's next? If I'm a company, I can invest R&D dollars into improving components. Which one should I improve? So it will never tell you this component is the problem. It will tell you this cycle is the problem, right? Because essentially, if you have things in a cycle, there's not one single point of failure, right? So it tell you, this is the cycle that you need to improve. Well, you also had like a broader question, I think, which is this all to design? Is this design in general? Well, this is part of it, right? So this is this is quantitative functional requirements. These are things that you can write down with numbers, right? In engineering, well, there's like very qualitative design problems. Also, there's something called verification, which is like I have a spec and do I guarantee that the spec works, and am I building the things right versus am I building the right things, right? And those are whether something is correct or not, that's really like out of the kind of computational realm, right? Of course, you need to think about this integrated into the broader like engineering practice.
There's a distinction between a closed system and an open system. Closed system, you control everything inside it. You're sort of this objective observer. You can spin up 2 versions of it and see which one's better. An open system is one that you're part of. You can't just spawn a second universe, or a second Earth, right? And yet you'd like to engineer sort of the direction that this large system will take on. I'm not sure what question to ask here, but it might be something.
No, so let me tell you. So I think here,
Does this account for closed systems only, or how does this work?
I think this is very good for, so here models are not that important in the sense that, so what you care about is like this input-output relation that you can imagine it's empirically measured, right? So the usual objection is like, yeah, this is a nice thing, but it assumes that you have a very precise model of the thing that you're building, right? Here, not really, right? Because any of those things could be like analytic, but it also could be, could be like really measured, like really like you like a spreadsheet, of functionality and resources. This is what we measured, and you can put also the error bounds, right? So in the realm of modeling techniques, this is very sympathetic to kind of empirical data, empirical results, right? It doesn't have strong assumptions about models. You can also take, you have the empirical model and the analytical model, and you can take the intersection, right? Which is, okay, now something that I know works in practice and also according to my theoretical model. Because usually what happens is that you never measure everything, you never measure the corner cases, right? So you always need like a theoretical, analytical model for the corner cases that you don't see in practice. So, I mean, I give myself like a B+ here, like in the sense that this is very robust as a formalism.
Let's save the rest of the questions for the coffee and cookies we have afterwards. Thank Andrea again.
Thank you.